for this. And the trick is to always remember to mute while I'm drinking. So I hope everybody had a good break. Thanks for getting your assignments in for those of you who've got. Otherwise, if those of you who don't, you've got a bit of time left. Or if you absolutely need a little bit longer, you could email me. I won't talk about the assignment today. I'll probably talk about it when we next meet on, when do we meet? Thursday, I think. At which time I'll probably talk also a little bit more about what we're going to do for the rest of the semester. Today we're going to do some really quite interesting. Oh, actually, I've gone ahead of myself. So I just picked out the wrong thing. So just bear with me for a minute. Oh, I see what's happened. Oh, okay, I'm ahead of myself. I was about to give you lecture 18 rather than lecture 17. Okay, I'll do it that way. I was about to say we're going to do something really interesting. That's sort of true, but it's more true of next time. Yeah, okay. So what I'll do here is just want to show you something, the difference between the exponentials and the powers. Right, so what you can see here is two graphs. Well, you can almost see two graphs. These go from x, goes from 0 to 2. So x goes from 0 to 2. And the two graphs are 2 to the x and x to the power of 74. So this one's the 2 to the x is an exponential, and this one is a power, the x to the 74. The 2 to the x is in red, and so the exponential is in red and the power is in blue. And when you look at this graph, you see that you don't see the red, all you see is the blue. So it looks like the x to the 74. Well, if you think about it, when x equals 2, 2 to the 2 is 4. And where's 4? Okay, 4's somewhere down here, right down there. Whereas 2 to the 74 is a pretty big number. It's about 3 times 10 to the 20. So about 3 with 21 zeros after it. So really pretty big. And you don't see, so you see the blue, x to the 74, but you don't see the red there, 2 to the x. So you think, oh, the power is beating it, which it certainly is. However, we can go a little bit further. Let's suppose we go from up to 200. 2 is not very big, but 200 is pretty big. So what's 2 to the 200 versus 200 to the 70 power of 74? Okay, again. Okay. So the red is still moseying along, and the blue is overtaken. It's really much bigger. In fact, if we do this, here's 2 to the power of 200. That's a pretty big number. And 200 to the power of 74 is a really much bigger number. Okay, so the blue is the power at 2 to the 704, 200 to the 74. So that's the x to the 74 when x is 200. And the red, which you can't see, is a much smaller number in comparison. It's only 2 to the 200. Or we can go a little bit further. Let's suppose we go out to 500. Okay, the blue is still, so the power and the power in blue is at the moment much bigger than the exponential in red. You can't even see the exponential. Yeah. If we go out to 600, yeah, still the same thing. What if we went out to 700? Well, hang on a sec. This is interesting. Remember, the red is the exponential, the 2 to the x. It suddenly appeared. You think, what's going on here? So something is happening around 700. So remember that the 2 to the x, the 2 to the x is our exponential, and our x to the 74 is a power. So here's the power, here's the exponential. Okay, but something's happening. So what if we looked a bit closer around 700? So suppose we went from 600 to 700. Now you start to see what's happening. Remember, the x to the 74 is the power one, that's the blue. And the exponential is the 2 to the x, that's the red one. And you can see that up until nearly 700, the power is quite a bit bigger than the exponential. But around here, around 700 and something, the exponential starts taking off. You see how it's much steeper? It starts taking off much more rapidly. So if we up to 703, now you can really see what's happening. The x to the 74 is still the blue one. The x to the 70, so that's the x to the 74 in blue, and this one is the 2 to the x. And you can see that even though that the exponential was being beaten by the power, the x to the 74, for a long time, right up till nearly 700, eventually that exponential does take over. So it might take a little while, but it does take over. And as soon as it does, it takes over much, much, much more rapidly. So if we went from, let's see, if we went from 690 that's up to 703. Let's go up to 704. Okay. So the exponential in red is the 2 to the x is escaping. Let's just go up to 705. Much, much bigger. even bigger. Now you can see that the exponential is way bigger than the power, and it's just going to get worse, and it's just going to get a bigger and bigger difference the further out we go. This. No. Now you can see that there's a huge difference. So this is what we mean by exponentials growing much bigger or much more rapidly than powers. May not be initially so, but eventually it will be. I'm missing something. Document camera. Right. So exponentials and logarithmic forms. That first bit was really, in a sense, is more of an introduction to next week, to next Thursday. But when we do complexity, the idea is that what we just did is some algorithms have complexity that looks like exponentials, and some algorithms look like complexity or number of operations are like polynomials or powers. And if you've got an algorithm that looks like a power, you're in luck. If you've got an algorithm that behaves like an exponential, that depending on the amount of time it takes, you've got problems. But before we get that, we're going to continue with what we ended up with at the end of, just before the break, exponentials and logarithms. And we've got this idea that, and this is the really important one, x equals b to the y, and y equals log base b of x are two things that are exactly the same. And there's no difference. They have exactly the same information. So if you say that 8 is equal to 2 to the 3, then you can say that 3 is equal to log base 2 of 8. So when you say log base 2 of 8, you're asking yourself, 2 to what power gives you 8? Well, 2 to the power of 3 gives you 8. So the logarithm is this: what power do I have to raise 2 to get to 8? What's log base 32? What power of 2 do I need to get to 32? Well, 2 to the power of 5 is 32, so log base 2 of 32 is 5. We've got the exponential form and the logarithmic form. And they're just two different ways of saying the same thing. Yep. So if I ask you these sorts of questions, we've already done this. Log base 2 of 8 is 3. Okay. Log base 5 of 25. Okay, well, if I give you 30 seconds to think about it, you'll tell me. Okay, well, you'll tell me 5 to what power is equal to 25? 5 squared. So you could justify it because 5 squared is 25. If I ask you what's log base 2 of a quarter, you say 2 to what power gives me a quarter? So, because 2 to what power gives you a quarter? Well, you say minus 2, because 2 to the minus 2 is a quarter. Remember, 2 to the minus 2 is equal to 1 over, So that's a negative, so we make a reciprocal 1 over 2 squared and change the sign. 2 squared is 4. If I say to you 49 is equal to 7 squared, and convert this into the logarithmic form, you can't see it. So 49 equals 7 squared converted into the logarithmic form, you will tell me. I'll do a couple of them. What's the logarithmic form of that? And so I'll give you those three. Exponential forms, convert them into the log forms. Okay, so converting into log forms, log base 7 of 49 is equal to 2. Now this one's a bit trickier. Root 9. Root 9 is actually 3 to the half. So the idea is that you've always got to convert it into some sort of power, exponential. So log base 3 one of those days. Who saw my mistake? Thumbs up if you saw my mistake. Yep, a couple of people. Excellent. This should be 9 to the half. Sorry about that. Okay, so log base 9 of 3 is equal, so log base 9 of 3 is equal to 1/2. Here, 5 to the negative 1 is 1 over 5, so log base, what's the base? 5. What are we taking the logarithm of? 1/5. 5 to what power gives us 1/5? Negative 1. Yeah, sorry about that one. Now, some rather more interesting ones. Something like this. Y equals log base 4 of 8. What's y? Now this is a bit tricky. It's doable, but it's not straightforward. The idea here is that you're saying to yourself, well, 4 to what power gives me 8? Now that's a bit, 4 to the power of 1 is 4. So 4 to the power of 1 is 4. 4 squared is 16. We want something between 4 and 6. No, you can't say it. We want something, log of 8. 8's between 4 and 16. So the logarithm base 4 is going to be somewhere between 1 and 2. It's going to be a fraction. So it's not just a plain integer. And the way we attack it is that we recognize that 4 and 8 are actually both powers of 2, so that actually might help us. So what we do is something like this. So putting this into 8 equals 4 to the y, so 4 to the y. What's y? Okay, so 8 you recognize as 2 cubed. 4 you recognize as 2 squared. But this is 2 squared to the y. So we can rewrite 8 equals 4 to the y as 2 cubed equals 2 squared to the y. What's 2 squared to the y? Our rules of indices, 2 to the 2y. So what do we conclude? 2 cubed is equal to 2 to the 2y, so that 3 must be 2y. So that exponent must be that exponent. In other words, y is 3 halves, 1.5. So we've got log base 4 of 8 is equal to 3 halves. Or if you want, 4 to the 3 halves is equal to 8. Where's 3 halves? It's between the 1 and 2. So 4 to the 1 is 4, 4 squared is 16, but 4 to the 3 halves is in between. Actually, you should maybe check this out. So that's our answer. Let's just look at, if I gave you 4 to the 3 halves, you'd say, oh, that's equal to 4 to the half cubed. Think of it, 4 to the 3 times a half. Okay. 4 to the half is 2, 2 cubed is 8. So 4 to the 3 halves really is 8, if you want to think about it that way. Okay. So if I ask you then this, it's a bit different. Find x if log base 3 of x is equal to -1. So what would we put in there to make this true? I'll give you a little bit to, oh sorry, -2. This is basically a rewriting. Okay, so rewriting this in the exponential form, x, 3 to the -2 equals x. So x equals 3 to the -2. So we're just going from logarithmic form to exponential form. What's that? That's 1 over 3 squared. So make a reciprocal, change the sign. 3 squared is 9, so 1/9. So x is 1/9. And then finally, same sort of thing. Find the base if log of the base of 1000 is equal to 3. So again, rewrite this into exponential form. And if you write it in exponential form, this says the base to the power of 3 is 1000. So what's b? Well, you know that 10 cubed is 1000. So therefore B is equal to 10. So you're putting it into the logarithmic form, into the exponential form. And this one, you're just relying on the fact that you know that 10 cubed is equal to 1000. That's just a bit of knowledge off the top of your head. And so the base must be 10. So the only thing cubed which gives you 10,000 is 10. Okay, so that's more on logarithms. We can draw logarithms just like we drew exponentials and we drew powers. You can draw logarithms. So we're going to concentrate on log base 2. What does it look like? So there are a couple of ways of doing this. The first way is, what are some values of x? Write down what log base 2 of x is, and then plot them out. So log base anything of 1 is 0. Log base 2 of 2 is 1. Log base 2 of 4 is 2. Why? Because 2 squared is 4. 2 cubed is 8, so log base 2 of 8 is 3. Log base 2 of 16 is 4, etc., etc. And we go back the other way. We've got to be a bit careful about what x's we choose. We're going to try and choose x's which we can calculate the log of.